All right, so in this section here, we're going to talk about two tests, the direct comparison test and the limit comparison test. So they're both comparison tests. And basically what we're going to do is we're going to look at something that just looks slightly different from a series we already know. For example, 1 over 2 to the n is a geometric series, right? Because that's just 1/2 to the n. But the second you put an n in the top, this is not geometric anymore. However, it looks very similar to this one, so we might be able to compare the two and draw a result on this second one based off of the first one. 1 over n cubed is a p-series with p equal to 3, so we know that that converges, and if that converges, even this series right here is different. They're not the same series. The +1 is not a p-series anymore. However, you might think that they would behave very similarly, because the +1 in the bottom is not going to matter that much, and we might see that that might be true if we can compare the two. And then this guy here is really easy to integrate with an easy u substitution, but the second you make the n in the top and n cubed, now this is much more difficult to integrate, so we can't use the integral test on this. But we might be able to compare them because they look so similar. Because if something looks similar to something else, that's not a bad thing, right? It might mean that they behave similarly, but we have to decide, okay, how similar are they? And there's two ways to do that. The first one is the direct comparison test. This one is the easiest in how it works, but it doesn't always work very well. There are times when it does not work, okay? So what it says is that if you have two series and each term of an is less than every term of bn, so we have series A and series B, and if A is smaller than B, what we really mean is each term is smaller than B, then if the bigger series B converges, then the smaller series A converges. And if A diverges, then B diverges. And I'll give you a little picture over here to help you. So let's talk about this one first. So we know that B sub n converges. So let's imagine a series that is getting smaller, where the sequence, all the terms are getting smaller and smaller, and we're adding up all of these values, okay? And if this is Bn, and it converges, so the values are getting closer and closer enough to 0 that the series, the sum converges, and an has to be smaller than that. So if an has to be smaller than this, then each term has to be lower than the term of bn. So it could get really close, right? But it has to be smaller. So if an has to be smaller, then there's no way that an won't converge, right? Because if bn's are getting small enough to converge, then an's will be small enough to converge. A cannot like come up here and go out and start getting too big. So the smaller one is stuck underneath bn and has to converge. And so then the opposite way, when an diverges, so an is the smaller one, right? So let's start with an. If an diverges, so these are all, let's say these values are getting bigger and bigger and bigger, so when you keep adding them together, it diverges. If B has to be bigger than A, then if B was going to diverge, it would have to get smaller and smaller and smaller, right? But it has to be bigger than A, so it has to, each term has to be bigger than A, and so it's going to have to continue to get bigger and bigger and bigger and not converge. So that's the idea behind, so this is B. And so that's the idea behind the direct comparison test. So the first thing you're going to do when you're applying one of the comparison tests is you're going to find a series that looks like one of these that we already know something about. So here you can see this 3 to the n looks like a geometric series. So we're going to compare to the series 1 over 3 to the n. Because this guy looks very similar to this one, it just has a +2 in the bottom. Now, we have to know something about this series, so we want to make sure we know something about this series. This is a geometric series where R is 1/3, And if the absolute value of r is less than 1, which it is, then this converges. So this is a convergent geometric series. So we would assume that this guy would probably also be convergent because it probably behaves a little bit similar, even though it just has a +2 in the bottom. But we need to show that from the direct comparison test. And the convenient thing about 1 over 2 plus 3 to the n and 1 over 3 to the n is that it's very easy to see which one of these will always be bigger no matter what n is. So for each term, term by term, this guy is going to be bigger than this guy because the denominator over here, the only difference is that the denominator over here has the +2. So that's going to make the denominator bigger over here, which will make the whole fraction smaller. So because 2 plus 3 to the n is bigger than 3 to the n, then when you divide by 1 divided by 2 plus 3 to the n will be smaller than 1 over 3 to the n. So 1 over 3 to the n, we know this guy converges, and this guy is bigger than this one. So up here it says if the bigger series converges, Bn is the bigger one, then the smaller one will have to be converged. So since this guy is smaller, then by the direct comparison test, this guy also converges because it's smaller than 1 over 3 to the n, and 1 over 3 to the n converges. So now let's look at a slightly more complicated example here. 1 over 2 plus the square root of n. So this looks a lot like the series 1 over the square root of n, which is a p-series with p equal to 1/2. So this diverges by the p-series test because this is less than 1. So this is a divergent p-series. So it looks like that series. So we probably expect this to diverge, but we're going to find something interesting happens here when we compare these two. This denominator is bigger than this denominator, which means this fraction is smaller than this fraction. So here, this guy is the bigger series. So we know the bigger series diverges. Okay? Now down here at the bottom of this page is a nice way to kind of informally think about what the direct comparison test says. I kind of said it earlier. So the first part says, so B is the bigger series and A is the smaller series. So this first part says if the bigger series converges, then the smaller series converges. And the bottom part says then A is the smaller one, so if the smaller series diverges, then the larger series diverges. But what we have here is that the bigger series diverges, and this doesn't say anything about if the bigger series diverges, then the smaller series does something else. Because if the bigger series diverges, the small one could converge or diverge. Both things could happen. So we cannot use this comparison. It's not going to help us because it says the bigger series diverges. So what we need to do is, if we really do think this is going to diverge, because it looks like this one, we need to find a series that if we want to say that something diverges, we need to find a smaller series that diverges. So we need to find a smaller series that diverges. And we found a bigger series that diverges. So that's not going to be helpful to confirm what we think our suspicions are. So I'm going to look at a series here that looks very similar to this one, but it's not the square root of n, it's now just n, 2 plus n. Now this guy looks kind of like 1 over n, and in fact it's actually the same thing as 1 over n if you just change the index. So if we start here at n equals 3, because when n equals 1 here, plug in n equals 1, you'll get 1 over 3, and we go to infinity of 1 over n, these are equivalent series. So these are the same. So this really is the harmonic series right here. So this is remember the harmonic series is a divergent P series with P equal to 1. Because it's got a little 1 here, okay? So this is a divergent P series here because this is equivalent to this one. And if you are not convinced, just think about what the first couple terms of this one are. Plug in 1 and you get 1/3. Plug in 2 and you get 1/4. Plug in 3 and you get 1/5. Here, plug in 3 and you get 1/3. Plug in 4, you get 1/4. Plug in 5, you get 1/5, right? We just re-indexed it. We changed this and this just a little bit so that they are the same. Okay? And so that you can see that this is also the harmonic series, even though you're adding 2 to the bottom. Okay, so we know that this guy is a divergent P series because it's the harmonic series. So now let's compare this and our series. And these guys here, square root of n is smaller than n, right? You take 5, take the square root, you get a smaller number. Take 6, take the square root, you get a smaller number. So square root of n is smaller than n. So that means 2 plus n is going to be bigger than 2 plus the square root of n. And so if this guy has the bigger denominator, then it's the smaller fraction. So now what we've done is we've found a smaller series that diverges, right? So if the smaller series diverges, then the larger series must also diverge. So here we would say by the direct comparison test, our series n equals 1 to infinity of 1 over 2 plus the square root of n diverges. So it does exactly what we thought it did. We just had to find a series that was smaller and diverged. And this one did not work because it diverged, but it was bigger. Okay, so this one can be very, very easy when it's very obvious that you can compare term by term one series bigger or smaller than the other. Let's look at another type of comparison test that is, I think, my favorite. I think it's even easier. It does take just slightly more work, but it is very helpful when you cannot figure out term by term comparison. Like you look at you can't find a similar looking series that you can easily say this one's bigger, or maybe it falls into the same problem we just did where the bigger one diverges and you need a smaller one that diverges. So what this series says is as long as it only works if they're positive, so you do have to have positive series here, but if you take the limit as n approaches infinity of the ratio of the two series, and if that limit is finite and positive, so greater than 0 and not infinity, then the two series will either both converge or both diverge. So whatever one series does, the other one does. So you're still going to pick something that looks similar. So we're going to prove here that any kind of harmonic series, this would also work for what we just talked about, like 1 over n plus 2. That one was pretty easy to show that that diverged. But if you have like 2n plus 5 or 1 over 5n plus 2, right? As long as it's similar to the harmonic series, 1 over n, then it's also going to diverge. So we're going to prove that by using some constant a and constant b here. okay? So this is very similar to the harmonic series. And so you would expect that this would diverge because this guy diverges. Remember, this is the divergent p series with p equals 1 because it's the harmonic series. And so what the limit comparison test says, we're going to take the limit as n approaches infinity. And it doesn't really matter which one you put on top, A or B. I always put the more complicated one on the top just for kicks. So we'll call this guy, well, not just for kicks, just to make things easier. So we'll call the more complicated one AN, and we'll call this guy BN. So we'll do the limit of AN over BN, and then we'll flip the fractions and multiply. So we'll have 1 over AN plus B times n over 1, which is just the limit as n approaches infinity of n over AN plus B. And now these are both polynomials, degree 1, so they're growing at about the same rate as we go to infinity. So we'll look at the ratio of the leading coefficients for the answer. And so that would be 1 over A. So the limit here will be 1 over A. And they told us here that A was positive and B was positive because otherwise our series would not be positive. So since A is greater than 0, then 1 over A is greater than 0, and it's finite because A is a number. So then what that tells us is that it doesn't just say converges. Be careful, it doesn't say converges, right? But it says that whatever our series was and whatever we're comparing it to, they do the same thing. So this guy was a divergent P series, so this guy diverges. So we will say, and if you want to make sure that you are being correct about that and not forgetting this, because this is an easy mistake, you can say this guy and this guy diverge together. So having a finite and positive limit just means that they do the same thing, which is what we expect, right? We expected this one to also diverge because it looks so similar to the harmonic series. So anytime you have something that looks like that, you're going to have a divergent series. So now let's look at a few more examples of some good choices for what you can compare things to, especially for the limit comparison test. So let's say we have this big complicated series here. A good comparison would be 1 over n squared, because this part as we go to infinity is going to really trump whatever's happening back at the back. That part's not going to really matter, right? This is going to trump the behavior as we go to infinity. Same thing here with this guy. The n as we go to infinity is really going to trump the behavior, so we could compare that to 1 over the square root of n. When you have a polynomial over a polynomial, you want to look at the ratio of the leading terms and simplify. So here, if we wanted to compare something to n squared over n to the 5th, we would want to compare it to 1 over n cubed, because that simplifies down to 1 over n cubed. So this will behave in a similar way to 1 over n cubed. Okay, so let's do some examples like this. So here, if we look at these two guys, they're kind of individually kind of look like a P series. And if we write the ratio of just the leading terms and we simplify, we'll have 1 over n to the 3/2. And so this is what we want to compare this to. We will compare to one over n to the 3/2. And the reason why we'll compare to this is because this is a P series with P equal to 3/2. So this is converging because 3/2 is greater than 1. Always make sure you write the y, okay? This is important to write down when you're doing these types of problems, okay? Especially this part right here, that is greater than 1. So we know that this 1 over n to the third converges, so we would expect this would probably also converge, but we need to confirm that. And these are not easy. If we were to try to do direct comparison test, it would not be easy to directly compare these to see which one's greater or which one's less, right? That's not going to be easy to do. So that's why the limit comparison test is really nice. So what we're going to do is we're going to take the ratio, limit as n approaches infinity, more complicated one on top, divided by 1 over n to the 3 halves, ratio of the two series, flip and multiply, and then we'll have the limit as n approaches infinity. This will be n to the 1/2, so 1/2 plus 3 halves is 4 halves, or n squared. And then this will be 1 times n squared, so n squared plus 1. And now this is a really nice and easy limit because these are the same degree, so we'll look at the ratio of the leading coefficients as we go to infinity to find the limit. Those are growing at about the same rate. So this limit will be equal to 1. And this is positive and finite, so this is greater than 0 and finite. And so what this says is not necessarily the series converges, but that the series does the same thing this one does, right? So we would say, okay, so by the limit comparison test, I'm just going to say LCT, which you are totally allowed to do, then both this guy and this guy converge together. Because this guy converges. All right, so for this last one here, let's look at what series we should compare it to. So we have n over n cubed, and when we simplify that, that's going to be n squared. So we'll probably compare it to something with an n squared in the bottom, but we're going to have a 2 to the n in the top that's not going to simplify. So this guy is going to have to be what we compare it to. And this looks like a mixture of geometric and p-series, so we can't really do one or the other. But we actually know right away that this guy diverges, and you can tell that by the divergence test, or the nth term test, if we do the limit as n approaches infinity of 2 to the n over n squared. This is going to be an exponential function compared to a polynomial, so the top grows so much faster. 2 to the n will grow much faster than n squared, so this will be an infinite limit because the top will grow faster than the bottom. So this guy here, we say diverges by the nth term test. Because remember, as long as this is not 0, then that will diverge by the nth term test. If you get 0, it's inconclusive. So just a reminder of that. Okay, so this series we know diverges, and so we would expect that this one would also diverge, but we need to use one of our tests to confirm that. So let's go ahead and do that. So we'll do the limit as n approaches infinity of the more complicated one flip and multiply. And then we have some nice cancellation that happens here. 2 to the n divided by 2 to the n, that will go away. And so then we'll be left with the limit as n approaches infinity of n cubed over 4n cubed plus 1. And then these guys are both growing at the same rate because they have the same degree. So we'll look at the ratio of the leading coefficients, which is 1 and 4, to find our limit. So this limit will be equal to 1/4. Which is greater than 0 and finite. So we don't just say it converges, right? We look at what did our original series do. This guy diverged, so they both diverge together. So this guy and this guy diverge together. All right, so that is the comparison tests. As you can see, it's really important that you already know really well the stuff that we've been doing. So that's why practice, practice, practice is so important when we're in class, because if you don't know the p-series by now and don't know the nth term test for divergence, everything else just kind of builds on each other.